Each of the following reactions has been reported in the chemical literature and gives a predominance of a single product in synthetically acceptable yield. Write the structure of the product. Only monosubstitution is involved. Yep. In each case, unless otherwise indicated. Okay, number 1. Our reagents are HNO3, H2SO4, so our electrophile would be NO2 plus. Yeah. So where would the NO2 go? We have two highly deactivating substituents and one slightly deactivating substituent. So whenever you have different substituents, the least deactivating substituent will determine the regioselectivity of the substitution. Since chlorine is ortho-para-directing and the ortho positions are taken, the NO2 will go to the para position. So the product then would be this benzene ring, CO2H, CO2H. We have a chloro there, and para to the chloro we have nitro, O2N. Next, okay, we have an NH2, a CF3 which is highly deactivating, NO2 highly deactivating. Okay, 2 highly deactivating and 1 strongly activating, so the strongly activating will determine the substitution site. Since that is ortho-para directing and the para is taken by the NO2 and one of the orthos is taken by the CF3, it follows that the Br will add to that ortho position there. So the product would be benzene ring, CF3, and H2. We have nitro there. And ortho to the NH2, you have a Br. Okay, what are we missing there? We are missing a Lewis acid, FeBr3. But apparently, the reaction works without a Lewis acid. But normally, if you do an EAS bromination, electrophilic aromatic substitution, which is a bromination, normally you use FeBr3. Next. Okay, we have a deactivating substituent and another activating substituent. Both are ortho-para directing. Okay, so which is the more activating? The hydroxyl. So that then will determine the site of substitution. The Br will add to an ortho position since the para position is taken by the benzene. So the product is benzene with an OH, and at the para position you have another benzene. Now ortho to the hydroxy you have a Br. Just like the previous question, there is no Lewis acid. Apparently the reaction works without FeBr3, but ideally you want to put an FeBr3 there. Next, okay, this here is a nitration again, HNO3, acetic acid. Usually it's HNO3, H2SO4, but this time acetic acid is the source of your hydrogen. Yes, you still produce NO2 plus as your electrophile, and the NO2 plus will go on the ring. So both substituents are activating. Look at the ortho position. Look at this one, a shared ortho position. The problem with that position is this is a tert butyl and this is a tert butyl. You have 2 tert butyls there at the 1,3 position. So in between those 2 tert butyls, it's going to be like really hard to reach that carbon. So chances are the NO2 will add to that their para position because that carbon is farthest from those bulky tert butyls. So the NO2 will add That's the nitro position. Probably there or there. Okay, so product would be this. You have a tert butyl here, CH3, and then CH3. That there carbon is very inaccessible because of the tert butyl, so probably it's going to be added there, NO2. Orthopara. And lastly, we have H2SO4 and we have a benzene ring and we have an alkene. Okay, so our electrophile is what? We have a double bond, we have H2SO4. So H2SO4 is a source of H+. So when the double bond sees that H+, it will attack that H+, and the plus charge will go to the carbon second from the left carbon. So this reaction becomes benzene plus H3C, single bond C. Now the plus charge is at that second carbon, H, and then CH2 parentheses 5, CH3. Okay, so we have an electrophile and we have benzene, so the benzene will attack the electrophile. This is a substitution reaction. And finally, we get our product, which is CH. So the covalent bond is between that carbon on the benzene and that carbon on your other reactant, CH. You have a CH3 there, and then CH2 parentheses 5, CH3. So that is only from A through E. I think this question is from A through W.